Hello and welcome, ladies and gentlemen, to our lesson today. Today we're going to be talking about some greatest common factor and also difference of squares. The first thing that we want to talk about here is, like I said, greatest common factor. Normally it is abbreviated as GCF, so if you hear me talking about find the GCF of something, that means find the greatest common factor. So I wanted to start by reminding you guys what a factor is. So a factor of a number is a number that when multiplied by something else gives us another number. I know that's a little confusing, which is why I have these factor trees here. So if I were to look at all of the factors of 12, the number 12, I would say that 1 times 12 gives me 12. I know that 2 times 6 also gives me 12. I know that 3 times 4 also give me 12. So this means that all of these numbers here in the tree, 1, 2, 3, 4, 6, 12, all of these numbers are factors of the number 12. Now if I wanted to look at the factors of the number 15, I could break it up into this tree and say 1 times 15 is 15, and 3 times 5 is 15. These factor trees are actually complete. These are all of the factors of the numbers above. And so now, if I wanted to, so that's what a factor is. And now if I wanted to find the greatest common factor, what that means is we're going to be taking two numbers, say 12 and 15, that we already have them here. And if I wanted to find the greatest common factor between 12 and 15, I would want to find the number that is, I would need to find a number that is in both trees and is the highest number. Well, I can see that both factor trees have the number 1 in them. And in fact, anytime you're finding the greatest common factor of two numbers, they will always share the number 1. So that's not very impressive. So we actually, almost 99% of the time, we're going to want to find a number that is greater than 1 for our greatest common factor. There's a special name for numbers that their greatest common factor is 1, but we're not worried about that for today. So if I were to keep looking at my factor trees, you could also see that the number 3 is shared by both numbers. And then they don't share any other numbers that are larger than 3, so I can say with certainty that the greatest common factor, GCF, of 12 and 15 is 3. So the way that we're going to want to use this with what we're learning with polynomials is to simplify these polynomials, or factor them. This is one of the strategies that you can use to factor polynomials. So let's say I had 2x squared plus 4x plus 6. So what we just did is we looked at two numbers. We looked at 12 and 15, and we wanted to see what the greatest common factor was between them. We wanted to see what the biggest thing that they shared, that they had in common, was. So now we're going to do the same thing for this polynomial, only instead of just looking at two numbers, we're going to look at all of these terms. So we're going to look at 2x squared, we're going to look at 4x, and we're going to look at 6. So the first thing that I do when I'm trying to find the greatest common factor of polynomials is I look to see if they share any x terms. Like if every term has an x, and we'll do one of these in a minute, if every term has an x, then you can pull out one of those x's. And like I said, we'll go over that more in a minute. But this one, there's an x squared here in this term, there's an x in this term, and there's no x here. So not all of the terms have an x, so we can't pull that out. So the next thing that I do is I would look at the coefficients of the terms. So the 2, the 4, and the 6, which is the coefficient. It's the constant. So it's just hanging out here on its own. So I would look at this 2, this 4, and the 6, and I'd do really quick factor trees for these guys because they aren't that big of numbers, so I can just do this real fast. So I know that the factors of 2 are 1 and 2. I know that the factors of 4 are 1, 4, and then 2 times 2, or just 2. And then I know the factors of 6 are 1, 6, 2, and 3. So this time we have 3 numbers that we're trying to find that have something, in common. So we want to try and find the greatest common factor of 2, 4, and 6. So we need to try and find a number that's in all 3 of these trees that is the largest number. Like I said, all of them will always share 1, but that's not special. So we want to try and find something that's greater than 1. I can see that all of these trees have the number 2 in them. And because that's the largest number that they all share, this is actually the greatest common factor between these terms. So that means that I can pull a 2 out, or divide each of these terms by 2 to get our factored version of this polynomial. So what I'm going to do, since I know that 2 is our greatest common factor, I'm going to divide each of these terms by 2 and pull out this 2. So the way it'll look when I'm done, maybe this will be an easier way to explain it. The way that it'll look when I'm done is like this. And the reason it's going to look like this, we pulled this 2 out in front and we have what's left here in the parentheses. And how we get what's in this parentheses is by dividing each of these terms by what we pull out. And what we pull out is our greatest common factor. So we did these factor trees. We found that our greatest common factor was 2. We know that we can pull that out. We put that in the front of our parentheses. When we need to fill our parentheses, we take each of our terms and divide them by what we pulled out. So I have 2x squared divided by 2. We have some 2's that can cancel, which gives us x squared, which we can see is right here. If we do 4x divided by 2, we know that 4 divided by 2 is 2, which leaves us with 2x, which we can see is right there. And then when we do 6 divided by 2, that gives us 3, which of course is our last term. So that's why we do this greatest common factor. It helps us to factor our polynomials. And in fact, it's the first step that we should do when we are asked to factor a polynomial. One thing that's important to note is that not every polynomial is going to have a greatest common factor. And sometimes we're just going to do like we did in class, where we break our factor up and we do, this guy. This one we wouldn't do that, but this is the first thing that we learned in class. And so sometimes there won't be a greatest common factor to pull out. You'll just go right into that Lee-off, as we call it. So this one, if we're looking for the greatest common factor, like I said on the last problem, the first thing that I like to look for is to see if they share x's. The reason I like to do this is because I can just look at the terms without having to do any math and know that they share something. So this x cubed is really x times x times x. X squared is really x times x. And then our x term is just x over here. So I don't have to do any math to know that these have something in common, because x times x times x, its factors x times x times x, and x squared, when we, these are what multiply to give us x squared. So it's really easy to say, oh wow, each of these share a single x. And so we know that because they share this, we're going to pull that out. And now when we try and figure out what we're going to fill our parentheses with, again, we can divide each of our terms by what we pull out. So if we have x cubed divided by x, we have some x's that cancel, give us x squared. If we have our x squared divided by x, we have some x's that cancel, just give us a normal x. And then if we have x divided by x, that just gives us 1, because these x's cancel. So then we take what we just got from our divisions and we go x squared right here. We drop down our x and we put in our 1. So this would be the factored form of this polynomial. Now, there are times when you guys might get really big numbers and you don't want to build factor trees for them. So let's say you had like 128 x cubed plus, I don't know, 64 x squared plus, I don't want to do another one of those. Let's go like 100x. So you might be able to look at this and just know what your greatest common factor is, but because I'm not a human calculator like Mr. Sherman, I will not be able to do that. But the first thing that I would do is look at these and see if they share x's, and indeed they do. Just like our last one, we have an x cubed term, we have an x squared term, and we have an x term. So that means that I'm going to pull out something to the x, and I'll actually move it up here. We're going to pull out something to the x, and now I'm wondering what to fill in here and what else to pull out, really. So the way that I would do this problem, that I would approach this problem, is I would say that each of these terms, they're even. So I know that I can pull out a 2. So that's just what I do. I just pull out a 2 to start. And then I also pulled out an x. So if we were to do 128 divided by 2, that would give us 64. And if we do x cubed divided by x, that leaves us with an x squared. 64 divided by 2 is 32. X squared divided by x leaves us with an x. 100 divided by 2 gives us 50. And then x divided by x just gives us 1. We don't need to put that there. And actually we had a little too much room for our parentheses. So, like I said, I didn't know, looking at this original problem, what our factor was going to be, but I know that I can pull out a 2x. So now I see that each of these terms are still even. So I know that I can pull out another 2 from here. The way that we'd write that is we have our 2x that's already pulled out, and now we're going to pull out another 2, which we're going to multiply eventually with our 2x that we already pulled out. So now I have 32x squared. We didn't pull out another x, so this x squared will stay, but we are still dividing this 64 by 2 because we pulled out a 2. This 32 gets divided. we have 16x plus 25. Now I would look at this problem and say, are they all even? No, this time our 25 is not. So then the way that I like to work is I say, so I know that every number has a common factor of 1, but that doesn't help us because we could pull out a 1 all day long if we really wanted to, and that doesn't help us because if we divide all of these by 1, what stays in the parentheses is the same, and then when we multiply on the outside by 1, that doesn't help us. So we don't ever want to pull out 1s. And then so the first thing I do is I look for even numbers so that I see if I can pull out a 2. If I can't pull out a 2, I like to see if I can pull out a 3. And this one, 32 is not divisible by 3, so I know that I won't be able to pull out a 3. Then I look at 4s. Can I pull out a 4? I can pull a 4 out of 32. I can pull a 4 out of 16, but I can't pull a 4 out of 25. So I move on from that. I go to 5s. And then I see, can I pull a 5 out of 32? No. Can I pull a 5 out of 16? No. Can I pull a 5 out of 5? Yes, but it doesn't matter because I couldn't pull a 5 out of these first two terms. Now, if I got to 5s and I still wasn't sure, I would probably, if the numbers were small enough, go to factor trees. Now, the number 32 has a lot of them. Well, I guess, doesn't really have that many. Let's see, 4 times 8. Yep, and then, yeah, that's it for that one. So these are all of the factors of 32. And then I'd go to 16. We go 1, 16, 2, and 8, 4, and 4. And then we go to 25, which is 1 and 25, and then 5 and 5. So as we can see, there is no single number in here that every single tree has. There are numbers that 2 trees have, like 32 and 16, they both have 16. That's a pretty big greatest common factor. But because our 25 factor tree does not have a 16, we can't pull that out. So, like I said, if we look at all of these trees, there's no single number that's in every single one of them. So that means, actually, that we are done here with our factoring, with our greatest common factor part. Now, whether or not you could factor this further, I don't know. We're not going to worry about it. This 32 out in front here is really gross, but I did promise to tell you guys what to do with this. So, because we pulled out 2x, and then we pulled out an additional 2, it's important that we multiply these together. Because when we did our 2 steps, here, let's do this first. The first thing we did was we pulled out a 2x and we divided all of these by 2x. And then we pulled out a 2. We pulled out a 2 here and we divided all of these by 2. So what we did, we divided by 2x and then we divided that by 2. Now this is a little complicated, but if you have some number, so here's our gross polynomial, I'll put poly, right? We took our polynomial, we divided it by 2x, and then we divided that by 2 over 1, or by 2. Well, dividing is the same as multiplying by the reciprocal. I know that's a throwback. You guys might not remember that, but just trust me. And then so really what we're doing is we're doing our poly divided by 4x. So even though we did 2 steps, it's the same as dividing by 4x. So that's why we want to multiply these together, just like we multiply them here. So if we were to write this, like our correctly written out greatest common factor would be 4x times 32x squared plus 16x plus 25. There you go. So like I said, when I'm met with really big ones, I like to start with 2, see if they're all even. If I do, I pull out that 2. Well, actually, before I even do that, I like to see if they share x's. They do, I pull out an x. Then they were all even, so I pull out a 2. And then in this one, they're all even again, I pull out another 2. And then once I get here, they're not even, so I pull out see if I can pull out a 3, and then a 4, and then a 5. And then after 5, I either make trees or do something else, because at that point, my brain can't do it. So there's one more greatest common factor that I want to show you guys. And this one tends to trip people up, and it actually, if you understand it, it's going to help a lot. It's going to help a lot when we do grouping, which is the next factoring technique that we're going to learn. So if I have, let's say I have some polynomial, x plus 2 times 3x. And then I say that I have plus x plus 2 times 4x. Well, here, let's make this 4x squared. That'll be nicer. So we want to look at these two terms these two big terms, and you could distribute these if you really wanted, but if you're presented with a problem like this and you're asked to factor, don't distribute them. It'll be gross, I promise. So don't do that. We don't want to do that. Don't shoot the arrows, not this time. So we're looking at these two terms and we're looking at what they have in common. Well, if we were to distribute these, we'd get some gross polynomials. We'll say poly 1. We'd get some polynomial, and then we'd get plus some different polynomial over here, right? So we'd have our polynomial 1 plus our polynomial 2. The reason we don't want to distribute these is because we just have to factor them again, because we're looking for the greatest common factor of this polynomial and this polynomial. So when it's in this form, it's already factored. We want to leave it like this. And so, because this is how we want it, we want to see what these two terms share. And now some of you are probably saying, like, Mr. McGill, it's obvious what these two share. Some of you might have no idea. That's totally fine. But if we look at this, we're saying that, so this polynomial, poly 1, whatever it is when it's distributed, right now we have it as x plus 2 times 3x. And then this other polynomial, polynomial 2, we're saying that it's x plus 2 times 4x squared. Well, what do both of these polynomials share? X plus 2. And so just like we did with our numbers, we've identified our greatest common factor, so we want to pull that out. We're going to say x plus 2. And so before, what we did is we did x plus 2, and then we filled in our whatever was left over. This one we want to make sure to put what we pull out in parentheses, because otherwise we're saying x plus 2 times something, and really what we want to represent is x plus 2, the whole thing, times something. So now we want to take our x plus 2, our greatest common factor, and we want to divide our original terms to find out what we're filling our new parentheses with. So if we do x plus 2 times 3x divided by x plus 2, our x plus 2's are going to cancel. It's going to leave us with 3x. And then similarly on our second term, we have x plus 2 times 4x squared, which when we divide by x plus 2 is going to cancel. So then we're left with 4x squared. There you go. That's probably the most complicated factoring that we'll do, and probably the hardest for you guys to see, and that's totally okay. Like I said, we're going to practice it when we do some grouping. Yeah, so now I want to move on to difference of squares. So we saw this in class today, but I want to reiterate it. So if you are asked to factor a polynomial, like if you get a problem that says factor, the 4 steps that you're going to go through in your head, the first thing you want to do, you want to see if there's a greatest common factor, if there's something that all of the terms in that polynomial share that you can pull out in front of the parentheses. So like just what we've done so far. The next thing you want to look for is a difference of squares, which we're going to look for, which is what we're going to go over next. The third thing, like we talked about in class, Leoff or backwards FOIL, where you're given a trinomial and then we break it into 2 binomials. You guys were pretty good at that. This is the third step, and then the fourth step, we won't worry about it because that's grouping. That's the next thing. So when you're given a problem, it says factor. First thing you want to do, pull out the greatest common factor. You're not always going to be able to do it, but if you can, you want to. You want to do this first. The next thing you're going to do, you're going to look for this difference of squares. And then, like I said, you're not always going to be able to do a difference of squares, but if you can, you want to do it. And then if you can't, you want to move to this Leoff, and then if you can't do that, then we'll move to the next step, but like I said, we won't worry about that for right now. So, greatest common factor, difference of squares, Leoff. That's what we know so far. So, difference of squares. Difference of squares. This, guys, I think you're going to like this because I personally think it's really easy to identify. So most of the things that we're asked to factor have 3 terms. Be like x squared plus 5x plus 4, right? If you guys were asked to factor that, you'd go, oh yeah, it's, x plus 4, x plus 1, okay, right? You could do that. That's the third step. That's Leoff. There's also nothing that we can pull out here. I know you guys can do that. So most of the time when we're asked to factor, we're given 3 terms. The trick and the thing, what the trigger that should go off in your head that lets you know that you're looking for this difference of squares is if there's only 2 terms. So if I have x squared minus 4, this in fact is a difference of squares. Now, every time you have 2 terms, it does not mean it's a difference of squares. The way that you know it's a difference of squares is if your first term is x to an even power, okay? The reason that that works is because when we break it up, if we were to break this up, we're going to start with x's. If it was x to the fourth power instead of the second power, we could do x squared and x squared. If it was x, oh, don't erase with your fingers. If it was x to the sixth power, we could do x to the 3 and x to the 3. That's part of why this is called difference of squares, because our first term is a perfect square and our second term is a perfect square. And if our second term isn't a perfect square, then we can't do difference of squares. Now, to remind you, perfect squares are numbers that, when square rooted, give us a whole number. So, sorry, I know that looks a little confusing now. So this was our original problem. We know that the square root of 4 is 2, so it's a perfect square. When we square root it, it gives us a whole number. The square root of 9 is 3, so 9 is a perfect square. The square root of 16 is 4. 16 is a perfect square. There's a lot of them, okay? So if our first term is x to the even power, or something that also, when square rooted, x to the 6th, the square root of x to the 6th, x cubed, look at that. Okay, so if both of our terms, well, first off, if we only have two terms, and then second of all, if both of our terms are perfect squares, and there's this subtraction sign in between, that's why it's called the difference of squares. If you guys remember word problems way back when, I know they were gross, I know you guys didn't like them, but if you'll remember, when we were subtracting, we would use the word difference. When we were adding, we would use the word sum. This is not called the sum of squares. It is not called the sum of squares. This is the difference of squares, this subtraction, this minus sign, this hyphen, this sideways L, whatever you want to call it. This is very important, okay? So, difference of squares, two terms. Both of them are perfect squares, separated by a subtraction sign, okay? So, now, when we pull this out into two things, like I said, our first term is going to be the square root of whatever the first term in each of our binomials, excuse me, is going to be the square root of our first term. We said the square root of x to the 6th was x to the 3rd. So we're leading with x to the 3rd. Our last term is going to be the square root of our second term. We said the square root of 4 was 2. So that means we're going to have 2 and 2. Now what do we put here in the middle? We're going to put 1 plus and 1 minus. It doesn't matter how you do it. You could go x cubed minus 2 and x cubed plus 2. That's the nice thing about multiplication. We can flip-flop these guys. As long as this x cubed and this plus 2 stay in a parentheses, they can do whatever they want. They can move here, they can move there, they can go on top and do it, you know, top to bottom multiplication, whatever you want to do. I wouldn't recommend it, but you could do it. So, difference of squares. Two terms, both of them are perfect squares, separated by a subtraction sign. The way we find what they break into is we square root our first and second term. Square root of our first term is the first thing in both of our binomials. Square root of our second term goes into the second part of both of our binomials, and then we have 1 plus and 1 minus. There you go, guys. Difference of squares. It's that simple. I promise. Now, like I said, you're not always, when you have two terms, going to be able to do a difference of squares. If you have x to the 6th minus 4x, if we just add this little pesky x, we would not be able to do it because the square root of 4x is gross. Here, I'm going to write over stuff. The square root of 4x is disgusting. We don't like it. It's gross. So because it's gross, we don't want to do a difference of squares. There you go, guys. That's enough of my ranting about difference of squares. I hope you guys get it. I'll be posting a shorter video with a couple different examples for GCF and difference of squares. I hope you guys have a good night, and I will talk to you soon. Bye.